I also could not see. Okay, I think the slide started, so we will start. Okay.
You started? Okay, I did not get any message on my mobile.
Yeah, it started. Yes.
Automatically it started. Oh,
okay. Good afternoon to one and all present here. So I welcome all of you for the weekly lecture series jointly organized by South Asian Meteorological Association and SRM Institute of Science and Technology. I request Professor Someshwar Das, Secretary, South Asian Meteorological Association, to welcome the panelists as well as the participants. Over to you, sir.
Okay, thank you, Dr. Lakshmi Kumar. President of SAMA-SRM, Professor Ajit Tyagi Saab, Professor Pradeep Kumar, Emeritus Professor, University of Pune, and also today's speaker. Members of the organizing committee, distinguished participants, ladies and gentlemen, we welcome you once again on behalf of the South Asian Meteorological Association and SRM Institute of Science and Technology, Chennai, India. Well, as you know, today is the 16th and the last lecture of the series of the module on atmospheric physics and sub-module on cloud physics. Professor Pradeep Kumar, a well-known cloud physicist in India, is the speaker of the lectures on this subject. As you know, the entire lecture series is designed for capacity building of the people in the field of atmospheric, weather and climate sciences. Well, we had a distinguished panel of very senior professors and scientists from the accredited institutions who are experts in the field. They have delivered lectures on the fundamentals of the subject. The lecture series, as you know, is targeted to the postgraduate students and professionals of non-meteorological background who are interested in learning the subject of weather and climate sciences for research and operation. As you know, we already completed 15 lectures, including 4 orientation lectures, 4 lectures on atmospheric thermodynamics, 4 on atmospheric radiation, and 3 lectures on cloud physics. Today, we have also invited one of the EC members of SAMA from Pakistan, but unfortunately he has not been able to join yet. Hopefully sometime during the lecture he may join. So we can hear his remarks after the lecture is over, if he joins by that time. As you know, certificates will be given to the participants who have registered for the course and will complete the entire course with at least 75% attendance and successfully perform in an evaluation test, which is supposed to be conducted next week. So the lectures are live streamed, on the YouTube channel of SAMA. They will also be available afterwards on the YouTube for those who could not attend the course live. We shall try to have more interactions between the speaker and the participants in this lecture series. Please write your questions in the chat box. Our moderators will pick up the questions and at the end of the lecture, and it will be answered by the speaker. So enjoy the lectures and wish you all the best. Thank you. Over to Dr. Lakshmi.
Yeah, before I think going to lecture today, so I request Professor Ajit Tyagi sir just to speak about the relevance. So over to you, sir.
Thank you, Lakshmi, and very good afternoon to Professor Pradeep Kumar, guest of honor, and also a distinguished speaker of the day, Dr. Someshwar Das, and my colleagues in SAMA who have been playing key role in organizing this particular series of lectures. You see, we were a little apprehensive about planning when we're planning these lectures, that how it will be communicated and how well it will be received. But with the support from all eminent speakers, this series of lectures have been great success. We have received a positive feedback from all participants, and the amount of registrations that has taken place and the regular participation also of a pretty high number, considering that to sustain for 16 lectures series is a real challenge. And each lecture by eminent speaker was of great value, right from the orientation part of it, because we have participants from diverse backgrounds, so bring them on the same platform for meteorological applications. And we started with the fundamentals of atmospheric thermodynamics. That is the basis, and of these 3 modules, atmospheric thermodynamics, atmospheric radiation, and cloud physics. It is culminating now as the 16th lecture, and as Somesh has brought out, really these were very, very fundamental, at the same time very, very in-depth, covering all aspects of these subjects. I personally also was able to refresh many of my basics on these topics. So I'm sure it is benefited immensely to the young researchers, and particularly the capacity building in our neighboring countries, and even in India. Many institutions don't have faculty to cover these topics in a manner which is required as a fundamentals. So with the presentations and lectures by eminent scientists, I am sure that has been of great help to these young researchers and students. So overall, we feel happy and satisfied that something we could contribute as SAMA with the help of our eminent members and faculty members. And so we are thankful to each one of them who have spared their valuable time, and also SRM IST for, I think, all support. It has been a flawless, conducting all lectures on time with recording and making them available. It has been excellent. So thanks to the Lakshmi and his team in SRM for organizing in such a meticulous manner, and it gives us confidence to follow up with many more such. We are planning a lecture series on atmospheric dynamics to follow these physics part, and followed by many others. So this is, I think, good. So once again, I thank entire organizing committee and especially our speakers. And today's speaker is, as we know, eminent cloud physicist and scientist, and also a teacher, which is so important for grooming young researchers. And many of his students are working in leading labs of the world. So that is also very, I think, matter of great pride for us. So thank you so much, Dr. Pradeep Kumar, for delivering this series of lectures, and we look forward for many more associations and guidance as a mentor to the members of SAMA. Thank you, and we look forward for your lecture. Thank you.
Thank you, sir, for giving the relevance of this lecture series. So before going to talk, I would like to give some 2 announcements. Since we have reached the end of this lecture series, we would like to have your feedback on this lecture series on various aspects. So in this connection, we will be sending a feedback form to all of you tomorrow. I request everyone to kindly fill the feedback form and also write your comment, so that whatever the improvements that we can, it can be done from our side also. And second thing is, as we were telling that the evaluation will be done, and based on the evaluation, we would like to give the certificates. The evaluation pattern, the evaluation will be on April 29th. We will send all these details in email. It will be on April 29th, Saturday at 3 p.m. So it will be multiple choice questions. So we will send the details of this evaluation pattern by tomorrow, along with the feedback email. So with this, I request Professor Pradeep Kumar to proceed for his talk on much more awaiting topic, atmospheric electricity. Over to you, sir.
Is it visible now in the?
Yes, sir. Yes, sir. It is visible. Yes.
Okay. So today I'll be covering in the atmospheric electricity, lightning and cloud electrification, and a little bit of other things also. Now, atmospheric electricity, we can split into disturbed weather electricity when thunderstorms are basically present in the region. Or we can split it into fair weather region when there are no thunderstorms or no clouds, or it is a clear weather. So first I will take up the disturbed weather. Okay, disturbed weather when thunderstorms are present and when lightning is happening in thunderstorms. Every cloud is charged to some extent, and it has some value of electric field building up. And in a large cumulonimbus clouds, these field will reach the breakdown field value for the air. The air is a dielectric medium, and when it reaches approximately about when thunderstorms are present, if it reaches about 300 kilovolts per meter, then this dielectric medium can break down and it can become a conductor, so the current can flow in it, and that is what we know it as lightning. So lightning can be either within the cloud, that is between the clouds, or from cloud to air, and these are called as in-cloud flashes, or between cloud and ground, called as cloud to ground lightning discharge. So it is IC flashes or cloud to ground lightning flashes. Now if you look at the charge distribution inside the cloud, in a cumulonimbus cloud, you have the cloud going up to around, in a tropics, going up to about 16 kilometers altitude with a cloud base around 1 to 1.5 kilometers. And between -5 and -25 degrees Celsius isotherms, we have the main charging zone, and apart from this being a main charging zone, the net charge in this volume is predominantly negative. And above -25 degree isotherm, it is predominantly net positive. And you have around the freezing level a small pocket of positive charge. Now the predominantly positive charge, it can be approximately on an average about 25 coulombs, and the net negative charge around -25 coulombs, and a small pocket positive charge of about +5 coulombs. And remember, the main charging zone is between -5 and -25 degree isotherms. So this is the typical charge distribution on an average charge distribution in any cumulonimbus cloud. Now, let us come to this cloud to ground lightning. And cloud to ground lightning is initiated by a leader process, what we call it as a step leader, because it comes down from cloud to the ground in steps of approximately each step lasting about 1 microsecond, and during which the step will advance about 50 meters. And then there is a time interval between the steps of about 50 microseconds. Like this, so the steps will be coming down. And the step leader is believed to start with a local discharge between the main negative charge center and the small pocket positive charge. So as the step leader is coming down, and the whole time taken is approximately about 20 milliseconds for this to come down. And so this is lowering negative charges close, and by the time it is reaching the ground, and normally it will be coming to the sharp points on the ground, and upward discharge is initiated from the ground. Please, can you somebody off your speaker, because it is interfering with my.
There's meanwhile a video war playing out between the BJP and SPPU over Atikar. The BJP is fired.
There is somebody has a speaker on. So as the negative charges are lowered, then what happens is at the ground, the positive charges will be collecting, and it will go and meet this leader, which is close to the ground, in the form of a return stroke. And this return stroke will propagate up in a very short time, because this channel is already now a conducting channel. Because the step leader has made this channel a conducting channel. So it will move up pretty fast. So the charges are transported in a very short time, in about 50 to 100 microseconds, on an average about 70 microseconds. So because the charge transport happens very, very fast in a very short time, the current it will carry on an average is of the order of 30,000 amperes. It can reach as high as 150,000 to 200,000 amperes. Okay. So on an average, it will have about 30,000 amperes. So this is the return stroke. So a step leader followed by a return stroke. After the return stroke has ended, and in about 40 millisecond or something gap, if further charges are made available at the top of the cloud, that will come down again as the leader. And this is called as the dart leader. And by the time the dart leader comes down, it is followed by again a return stroke, which will again propagate up very fast in the order of about 750 to 100 microseconds. So in a lightning flash, there may be a sequence of such events, a leader followed by a return stroke. And normally most of the flashes contain 3 to 4 return stroke in this sequence. And the whole thing which you see is a flash, single flash like this, because your eye cannot separate out all these finer events which are taking place. So the whole thing you will see as a single flash. So this is again a lightning flash, which is photographed by one of my students. And so these are flashes, different lightning flash. There are so many channels which are opening up. Okay, it need not be a single one, because the charges are flowing down and breakdown can happen because of the high charges which are flowing down. So breakdown can happen with the air nearby. So it will not be a single lightning flash. There can be branches also. Not here also there are branches, very fine branches you can see. Okay. Now this is over a 30-minute period. The total amount of lightning which has happened at Norman, Oklahoma, which is again captured by one of my former students who is now working there at Severe Storms Laboratory. Over a 30 minutes, this is a stacked lightning, all those which has happened, which is the intra-cloud lightning, as well as the cloud-to-ground lightning discharges which has happened. So again, see, you can see this as it's a fraction of a second. So that is why you're not able to see the steps. This is, you see, it's a fraction of a second. So you can't, your eye cannot see the finer events which have contributed to this single lightning flash. Now cloud flash. Now cloud flash generally, that is the in-cloud flashes, they can happen between either if two clouds are there or within the same cloud, or there may be different cells inside a huge complex of clouds. So a cloud flash consists of generally a single slowly moving leader that travels between a positive and negative charge region of the cloud, or between the same cloud or between different clouds. And this may be followed by several brighter pulses, each lasting about 1 millisecond, typical of that which happens in a return stroke in a cloud flash. Now, cloud flashes generally take a longer time, and it is visible for a longer time. So it is moving, the charges are being transported at a much slower speed. So therefore, the current is in a cloud flash is much less compared to that of a ground flash. So these are the cloud flashes again, so this is again how the cloud is getting illuminated in a night sky with the flashes, in-cloud flashes which are going on. This is again now if you can see this flash, you see the finer pulsating events which are taking place. These are all the millisecond pulses which are happening, which is equivalent of the return stroke in a cloud to ground flow. of a cloud to ground flash and the intra-cloud flashes. Okay, I'll play this again. So you see the finer events which are happening. Okay, and it has lasted for a much longer time compared to the ground flashes. Now here you can see the lightning flash coming down in steps. So it's all branches, steps. These are all coming down in steps. And finally, a return stroke has happened. So now typical values in a cloud to ground lightning flash, total duration of the flash, approximately about 20 milliseconds, average current 30,000 amperes. The breakdown electric field required for this lightning to happen is about 300 kilovolts per meter. And average temperature in the channel can be about 30,000 degrees Celsius, and average power in a channel is about 10 to the power of 9 watts. Now thunder, that is what you hear. So the return stroke in the cloud to ground lightning raises the temperature of the lightning channel to over 30,000 degree Kelvin in a short time. In about 20 millisecond to 20 to 30 millisecond, your channel temperature has gone up on an average to 30,000 degree Kelvin. It can be much higher than that. And so when such a high heating is happening, the pressure in the channel increases to 10 to 100 atmospheres. That is 10 to 100 times your normal pressure. And this high pressure, the high pressure in the channel then expands suddenly and creates a powerful shock wave. And that is sometimes, if it is happening nearby, that is when you hear all your glasses, window glasses and everything vibrating, and which travels faster than the speed of the sound. And when it moves further away, you hear it as a thunder. Now, those were the discharges which are you're seeing with your eye in almost in every thunderstorm. All of you must have been watching it, and you must have watched your cloud to ground, intra-cloud lightning, you heard the thunder and everything. But then there is something which you might not have seen. Most of us have not seen, which is the upward discharges. People for centuries have been suspecting of upward discharges from the top of thunderstorms. And the first report of an upward discharge came from an airborne observer on board a Canadian Pacific airline flight in the vicinity of Fiji in February 1950. Okay. But there have only been reports and no photography. Nobody could capture it on a video or on a photograph. The first image of one was captured only in 1989, and that too accidentally during the testing of a low light television camera by a group of researchers from University of Minnesota in USA. They were actually filming a star field occurring about 250 kilometers away from them on the northwest side of Lake Superior. And this star field was above a distant thunderstorm. And on July 6, 1989, at 4:14:22 Universal Time, the camera observed a twin upward flash originating in distant cloud tops. And this phenomena, which is now termed as a red sprite, was captured for first time on a camera. This is not the first image. This is the first color image which was taken. It is from University of Alaska, Fairbanks. So this goes all the way till about 90 kilometers altitude. So this is again a red sprite which is observed from the International Space Station. It's observed here. I'm sorry, the blue image circle has shifted. And this is a thunderstorm, active thunderstorm here. There is a lightning which has happened. That is why this storm is illuminated. And this is this one, and this is the expanded one which is here. Okay, this is from the International Space Station. Now about red sprites. Red sprites are actually coincident with cloud to ground lightning discharges. And sprites are predominantly red in color. The brightest region lying in the altitude range of 65 to 75 kilometers. And below the bright red region, blue tendril-like filamentary structures often extend downward to as low as 40 kilometers. This comes down, these blue tendril-like filaments come down to almost 40 kilometers. And current evidence strongly suggests that sprites preferentially are occurring in the decaying portions of thunderstorms and are correlated with large positive cloud-to-ground lightning strokes, which is lightning strokes or discharges which have greater than 50 kiloampere of current. Only those lightning, and that too, those predominantly positive cloud-to-ground lightning, they are only able to produce these red sprites. Now, when red sprites was being investigated, two other upward discharges were discovered. One is the blue jet and another is the blue starter. Blue jet, they are occurring above thunderstorms, and blue jets are deep blue in appearance and reach maximum altitudes of 40 to 50 kilometers, which means they are at much lower altitude than the red sprite. Red sprites normally terminate, their lower altitude is about 40 kilometers, whereas blue jets have a maximum altitude of 40 to 50 kilometers. It is conical in shape, but red sprites have different shapes. They can be in variety of shapes. And so their horizontal width is less. The cone is observed to flare at the end, and as such, it will be resembling a trumpet. And then blue starters occur at much lower height. They can reach only a maximum height of about 25 kilometers starting from the top of the thunderstorms. So these were other two phenomena which were discovered when they started investigating more into the red sprites. So this is a blue jet over India, taken on board the International Space Station. This is astronaut Andreas Mogensen, caught a rare glimpse of a blue jet over India. This is somewhere over central India. Now, all these events, these red sprites, blue jets, and blue starters, they are called as transient luminous events. Now, these are red sprites. Now, red sprites, minimum altitude 40, maximum around 90. The brightest region lying between 65 to 75 kilometers. And their horizontal widths are very, very wide. They can be as wide as 25 to 50 kilometers. They are very wide, because why it is happening is because if at the surface, if you have a ground discharge, which is only 1 meter or something, but when you're going higher and higher in the atmosphere, the pressure is becoming less. So streamers which would have been generally been only about 1 meter or few meters wide, they would occupy several tens of kilometers as it is going higher because of the low pressure. Okay. So this is associated with a cloud to ground discharge, generally when a very high cloud to ground discharge. So it can happen from the positive, when positive current charges are lower, or towards the end of the storm when these positive charges had come down because the negative charges have precipitated out. So towards the end of the storm, you're getting positive discharges, and with much larger currents, that is, it should be greater than 50 kiloampere, then only this red sprites can occur. That is because when this current is lower, there will be an electric field drop between the ground and the upper atmosphere. So that electric field, when you are integrating it, that is enough to cause the molecules to get excited and then give you these discharges. Now, blue jets, they are conical in shape, maximum width around 5 kilometers. And blue starters, again, blue jets can go to 40 to 50 kilometers altitude. Blue starters can go to about 25 kilometers altitude. And its width, horizontal width is also very less. These are all conical shape, and cone, which is trying to flare out at the end so that it looks like a trumpet. Now, these are the representative values of red sprites, blue jets, and blue starters. Color is red. Blue jets are deep blue. Minimum altitude of red sprite 50, 20. These blue starters can be from the top of the cloud. Maximum altitude greater than or equal to 90. The blue jets are 50 and this is 25. Width is 25 to 50 kilometers. Duration of red sprite is approximately 300 millisecond. It can vary. Okay, sometimes it can be just brief, around 5 to 10 milliseconds. Blue jets are 250 milliseconds, and blue starters are very brief. Association with lightning, or they are often follows the cloud to ground lightning with positive currents. And blue jets often follow blue starters, and blue starters are not coincident with any lightning discharges. Now, lightning discharges gives out electromagnetic radiation in the entire electromagnetic spectrum, starting from X-rays, gamma rays, all the way in the whole spectrum, with a peak power lying in the very low frequency region in the range of 3 to 30 kilohertz. Now, by detecting these electromagnetic radiation, we call it as these are spherics. We call these electromagnetic radiations as which are caused by lightning as spherics. And by detecting this electromagnetic radiation, it is possible to determine the location of a lightning source. So this is made use of for setting up your lightning location systems. So this is the detection frequency. In this frequency, 10 kilohertz to 12 megahertz is used for this lightning detection. This is a detection system which is used by the Indian Institute of Tropical Meteorology of the Earth Networks application. And here the 10 kilohertz is used for detecting ground discharges, and the highest frequency of megahertz, 1 megahertz to 12 megahertz, are used to detect cloud discharges. So because these discharges, they produce the ground discharges, their peak power is in the VLF range, and the cloud discharges is in the very high frequency range, in the megahertz range. So therefore, from a discharge, from looking at the detection frequencies, you can separate out the cloud discharge and the ground discharge. And these are the whole network which is there in India. It's about 82 Earth network lightning sensors are installed at different locations by the Indian Institute of Tropical Meteorology. So if any three, if a lightning has taken place and if any three sensors detect that, they can exactly find out to very accurately to a very few meters where the lightning has struck. And this is courtesy to the India Meteorological Department, the lightning which is detected from those networks. Okay. So here the time is changing, and during the the color is changing. So last 10 minutes, last 20 minutes, last 30 minutes, where exactly the lightning has occurred on this particular day. Now, what is the use of this lightning detection network? Why do you require it? One is weather forecasting. One is immediately, which is called as a nowcasting, which is what is going to happen now, immediately, in the near time. So for this is used. Second is electric power utilities, preventive measures for an approaching storm. Because generally when you see the lightning has got such a high current, so that can induce surge in your electrical power lines. And this surge, most of you must have felt that when lightning is happening, you must have seen the flickering of your lights. So that means it's a surge current. So sometimes this surge current can trip the entire power grid. So therefore, they can take the preventive measures for approaching storms if they know that your lightning is coming. So if your lightning has started nearby, as the storm will be approaching towards you, the warning can be given. So they can take the preventive this one. Air traffic control, they can reroute the aircraft. If there are any thunderstorms around, they can reroute the aircraft around severe thunderstorms. Airports can suspend high-risk activities like fueling. Fueling is a very high-risk activity because any lightning strike is going to cause a huge disaster to the whole airport. So they can stop the fueling when it is happening. Insurance, because a lot of insurance claims will be coming due to lightning as the cause of property damages or fire. So insurance sector need the information on where exactly these lightning have struck, so that if any damage claim for it is coming, they can look into it. Then power sensitive operations, because if you're running some huge computer programs or something and you don't want any power breakdown to happen, then you can switch on to your generator backup power early. So any power sensitive operations, if you know that your thunderstorm is approaching, then you can switch to backup power early. Hazardous materials, especially in where your explosives are stored, or your gas, your cooking gases, all these refineries. So you can warn the personnel working near explosives and flammable material to evacuate and don't be around that area. Outdoor sports, because if you are playing outdoor sports, you need to run to safety, because lightning generally can strike tall objects. And when you are in a field, the players may be the tall objects. So therefore, you want the players to move away from outdoor sport activity. Then launch facility, you have to monitor for the safe conditions for shuttle and satellite launches, because they will be having huge amount of fuel and standing out in the open. And so, and then forestry is important, very, very important, because millions of hectares are lost in the forest fires, which are initiated by lightning. So once you know where the lightning has occurred, you can dispatch helicopters to check whether any forest fire has started. So that is from the ground detection network. Many of the countries are having now this network of ground networks of lightning detection. Several of the advanced countries have it, and several countries in Africa have it now. So lightning detection from satellite. Now lightning imaging sensor, which is the LIS, was placed on the TRIM satellite, which what it does is, because this on the left side, which I'm giving, is the spectrum produced by a lightning discharge. Is all the spectrum which is produced by different excitation lines, okay, of oxygen and nitrogen. So these are all the excitation lines, which is, if you put a slitless spectra, you can get the spectrum. Using a prism or something, you can get a good spectrum. And this is so the satellite lightning imaging sensor on the TRMM satellite was monitoring this 777.4 nanometer oxygen excitation line. Okay, because they are illuminated well above the background levels, because your background may be your sunlight or all the city lights which are there. So this is the 777.4 line, which I am pointing here. Okay, this is emission. This is actual emission. Okay, and this is the spectrum which is plotted. A typical example of a cloud top lightning spectrum. So this is monitored. Okay, so this is a climatology of the TRIM satellite between 1998 to February 2013. So over the oceans, you have very less lightning. Okay, so this is pink is 10, less than 10. Okay, and most of the lightning is in the land. Okay, now this TRIM had a viewing only of the plus and minus 35. So that's why only you're seeing in this region. Okay, so you have this is North America, this is the US. So all this black is the highest. Okay, so this black and gray regions are the highest, then followed by red. So you've got a black region in South America, very intense lightning, and you've got in Central Africa, and you've got in South Africa, and over the Indian region, you've got over the Western Himalayan region, and over the Eastern region. And then you've got again small pockets in China. Okay. So this is a climatology. Now satellites, because since they are passing by, it's very good for constructing the climatology or looking at the climate, how it is going to vary year to year, how it is happening and everything. But actually for forecasting and warning purposes, you require the ground-based sensors. So now what is the present status? Because TRMM has stopped working in 2014 or 15 April. And so what is the present status? Present status is a lightning imaging sensor was placed on the International Space Station on February 2017. And it is giving more coverage because it is going from plus minus 55 degree north and south latitude. Whereas TRMM covered only between plus minus 38 degree north and south latitude. So this is now the lightning climatology between the International Space Station LIS and the TRIM LIS. It's more or less the same, but with period to period, there will be variations. but more or less all this red and the spots, these are the weak lightning over the oceans and higher lightning over the land regions. So that was the disturbed weather electricity part. Now let me come to the fair weather electricity part. Now you have your disturbed weather here. You have the lightning, which is lowering negative charges, and you have a cloud, which is a positive charge. Now this is your Earth and your ionosphere. Now your ionosphere, Earth is at a zero potential, or it is at a negative potential with respect to ionosphere. And ionosphere on an average is at about 240 kilovolts positive with respect to Earth. This can go as high as 400,000 volts. Okay. Now lightning lowers negative charge, so your ground is negatively charged. And there are leakage currents from the top of the Earth which are happening because your Earth is receiving continuously radiation in the form of cosmic rays and radioactivity from the surface of the Earth. So there are ions in the atmosphere which are there, which will be giving you the conductivity. So because there is a fine conductivity which is happening, which is there, so there will be leakage current which is going on and which will travel through the ionosphere until it will come down in the fair weather region as a fair weather current, which is of the order of picoamperes, which is of the order of 2 into 10 to the power minus 12 ampere per meter square. So if you take a unit area, you'll have a picoampere of current flowing in that, which is a kind of a constant current in the whole of the atmosphere. Now these currents and these ions will be driving an electric field closer to the Earth surface, which is about 100 volt per meter, and this is a downward directed electric current. So that is why it is a minus sign is put here. It is 100 volt per meter closer to the surface of the Earth. And as you are going up, this electric field value decreases and goes to millivolts and microvolts as you reach the top. But the potential is increasing. It goes up to about 240 volts, 240,000 volts. Okay, and the field will be decreasing. So this is basically, I'm giving you a rough idea about the fair weather electricity because I need to use this later in my talk. So there are so many other parameters also for this, which I'm not touching upon because in this short lecture, I cannot touch upon all the other components of the fair weather electricity. It is a huge component is there. So I'm basically touching upon these things. So thing to remember is that Earth is a negatively potential or a zero potential. And since it is at a negatively charged, that closer to the surface of the Earth, there is an accumulation of positive ions or positive charges on closer to the surface of the Earth, which forms like an electrode layer closer to the surface of the Earth. So this we will make use of. Okay. So this is about the fair weather electricity. So now let us come down to now the thunderstorm charging mechanisms. Thunderstorm charging mechanisms, there are several theories because it has to all come from theories because it is a phenomena which is happening high above you and there are no ways to go and probe it and explore it and find out actually what is actually happening inside. Okay. So all these have come up from the theories. So several theories have come up over the last 70 to 80 years. And I will split them basically into two. This one, convective charging theory and precipitation powered mechanism. Now, convective charging theory assumes that the precipitation particles need not be present inside the cloud for the charging to develop. Okay. So the charge which has to develop is you need to have a top of the cloud which has to have a net positive charge, which means if you take all the precipitation particles and integrate them in that volume, it should have a net positive charge. You may be having positive and negative, but overall it should have a net positive charge. And in the central region, it should have a net negative charge between about -5 and -25. It should have a net negative charge. And at the freezing, near to the freezing layer, you can have a small pocket of positive charge. So convective charging and the precipitation powered, I split it up to inductive charging and the non-inductive charging. Non-inductive charging, again, I am touching upon only two mechanisms. Let me tell you that there are several theories which are there. Okay, these are only the few important ones which I have picked it up. Okay, now what is the requirement for any satisfactory theory? Because even though there are so many theories, most of them don't satisfy the requirements. So there are requirements to put up any theory. So the requirements for a satisfactory theory, which was given by Saunders in 2008, it's a very good review paper. I've given the reference at the end. So time available for electric field generation of about 300 kilovolts per meter is about 30 minutes. In about 30 minutes, the cloud should be able to generate 300 kilovolt per meter electric field. The charge generation should produce about 20 to 30 coulombs per lightning flash. And charge separation should occur in the region between 0 to minus 40 degrees Celsius isotherm in a radius of about 2 kilometers. And the main negative charge center is between minus 5 to minus 25 degree isotherm. That is, we call it as a main charging zone. And the main positive charge center is a few kilometers above the negative charge center. And the lower pocket positive charge is close to 0 degrees Celsius. And the first lightning discharge should occur within 12 to 20 minutes of the detection of large precipitation particles on the radar. So moment the radar has started detecting large precipitation particles, within about 12 to 20 minutes, you should see the first lightning discharge, which means within that time, you should have reached this breakdown field. This is the required breakdown field for lightning to happen. And so for that to happen, the charging theory should be generating about 5 to 30 coulomb per kilometer cube, leading to a charge generation rate of 1 coulomb per kilometer cube per minute. So these are the stringent requirements for any theory to be considered for the charge generation mechanism. So let us look at the convective charging. Now, convective charging, what it is assuming, because I told you in the fair weather region, the earth, closer to the earth, there is an accumulation of positive charges. So these positive charges, when any air parcel is forming and it is going up, these positive charges will be going up in this air parcel. And when there is a pocket of positive charges here, that will be attracting all the negative ions in the atmosphere. And so these negative ions, they will be coming down and they will be getting pushed because you have the updrafts which are going from the base of the cloud. So as it is a growing cloud, so these negative charges will be getting pushed and they will be all be getting attached to the precipitation particles, which will be finally forming through the condensation process. So these ions or these charges can get attached and thus forming the region of positive charges and a region of net negative charges. So this is the convective charging theory, which was proposed. Now the precipitation powered mechanism, which is an inductive charging mechanism, which means there should be precipitation particles in the cloud for the charging to happen. Now, when you have a fair weather electric field, those are downward directed field, which means ionosphere is positive and earth is negative, so the field is downward. So if you're putting a raindrop in that electric field, it will be polarized. The raindrop will get polarized because of the H plus and the OH negative ions. So what happens is the polarization happens with the negative charge on the top side of the drop and the negative positive charges on the bottom side of the drop. So when these drops are approaching each other and colliding, so the lower positive will cancel with the upper negative. And the negative charges being, as it is coming down, this is the heavier drop which is coming down. So they will come with a negative charge and the lighter one which is going up will go up with a positive charge. So this is the inductive charging mechanism. Now, the next is the splintering of drop during the freezing process. So when a drop is beginning to freeze, generally as your experience from your freezing of water in the refrigerator, it will start freezing from outside. So outside temperature is colder, inside is warmer. So the warmer one will have OH negative ions, which are heavier, and the lighter ones, which is the H plus ion, they will move to the outer shell. And when the drop freezes, once this outer shell is this one, and when the inner shell is beginning to freeze, it will expand in volume. Okay, because ice generally occupies more volume than the liquid. So when it expands, this outer shell will be breaking. So shell will have all splinters, and that will be going up with the positive charge, and the shell with the this one, the inner core which is frozen, which will have negative charge. So this is how the splintering of drop is supposed to work. Now, what does the field observations show? Field observation shows that lightning happens in clouds which have mixed phase precipitation. Because if you have seen, if you're aware of the monsoon situation, you will see that when monsoon has set in and the clouds are not so deep, you don't hear any lightning. And similarly, when it is only you're getting snow and everything, you don't see lightning. So lightning happens only in clouds which have a mixed phase precipitation. So you have got which are the warm cloud processes and the cold cloud processes. So mixed phase is where you have ice, supercooled droplets dominating. Okay, that is a mixed phase, and water vapor. Okay. So these are the observation. Observation shows that lightning happens only in clouds which have a mixed phase precipitation. So this ice crystal Graupel collision explains that the largest charge transfer occurs during interaction between a vapor-grown ice crystal with the Graupel. Graupel, I have already told you what is Graupel in my previous lecture. And so when this is interacting with the Graupel in the presence of supercooled droplets, then there is a large amount of charge transfer happening. And the effectiveness of this thunderstorm process comes from extensive laboratory experiments, aircraft and satellite observation. So this theory is now the most and the well-accepted theory for thunderstorm electrification, which is the ice crystal Graupel collision. Now the whole of this theory started with the laboratory experiments which were conducted by Reynolds et al., which is published in Journal of Meteorology in 1957, where they rotated ice spheres, which is supposed to represent Graupel, in a cloud of ice crystals and supercooled droplets at minus 25 degrees Celsius. And they found that when ice crystals hit and bounced off a Graupel, the Graupel got negative charge and the ice crystals got positively charged. And they found negligible or practically no charge transfer when collisions happen only between ice and ice without supercooled presence of supercooled droplets. So basically, the supercooled droplets have to be present. So a Graupel means there is a rhyming happening, which means the supercooled droplets are colliding on the ice crystals and they are freezing. So only when that is happening and ice crystals are colliding with the Graupel and separating it out, then the charge separation is happening. So this whole series of experiments started with the work of Reynolds et al. When later two groups, one at Manchester, United Kingdom, and another at Hawaii, USA, did experiments for almost 40 years continuously. And they came up with the broad results. There are so many final results, but I will come to the broad results. So this is from the Manchester group. This is the charge per event. Charge per event means one event is when an ice crystal is colliding a Graupel and bouncing off. That is one event. So this is the charge per event, and the charge separated out is in the order of femtocoulomb. One femtocoulomb is of the order of 10 to the power of minus 15 coulomb. And the main important thing is, as there is the charge is rising with temperature, and then it is coming down, and then there is a charge reversal temperature which is around minus 18 degrees Celsius. Okay, this is from the Saunders group in Manchester, and this is the result of Takahashi group in Hawaii. Both of them have done experiments for more than 40 years. Okay, and this is Takahashi group's broad results. That is, there is a negative charging region, and these are all positive charging region. This is the temperature which is varying on the x-axis, and on the y-axis is the cloud liquid water content. So this is a function of cloud liquid water content also, not just temperature and the cloud liquid water content. So a lot of experiments were conducted. Several students have worked in these labs, bringing out very, very important results. So I'm just highlighting a few important results. That is, this is again, the charge transfer is dependent on the cloud water content. It is dependent on the size of the cloud drops. It is dependent upon the velocity of the colliding particles. And now this is again a later summary by Saunders group. That is, this is again with the function of cloud water content, how the positive charging regimes are there, how the negative charging regimes are there, and again the positive charging regimes are there. And this is, I worked with the Saunders group for my postdoc during 1986 to 88 at University of Manchester, and the finding that we made was that even if two particles are interacting, whether it is ice crystal and graupel, the surface that is growing faster will charge positive. That was an important finding that we got from our work. Then at Pune University, we did the experiments because the cloud is never pure, because all these experiments were done earlier. Manchester group and the Hawaii group both did with pure water. So what we did in Pune is we did it with trace chemicals in concentrations which are found in rainwater. Now this is a chamber which is a walk-in cold room which can reach as low as -30 degrees Celsius. So I have 2 tubes which are here in the side. So on one tube, I have a gold target which is spherical in shape, on which a graupel is grown. And this graupel target is connected to an amplifier. And in this, in this chamber, I have a cloud of supercooled droplets and ice crystals which are grown in the cloud, and which has a trace amount of either ammonium sulfate or sodium chloride. And then once there are very few crystals left in the cloud, because the cloud is growing and falling off, and there are very few crystals in the cloud, I draw these crystals past this tube so that they hit the graupel, and when they bounce off, charge is transferred. So momentarily I turn it on so that the crystals are hitting, and I have another tube with the bottom wherein I can count the number of crystals which are there in a unit volume, so that I can know that is how many crystals have exactly hit this and what is the. So this is the typical amplifier output, where this is my background noise, and when the cloud of crystals and supercooled droplets have been drawn past the graupel, when it collides with the graupel, this is the charge which has been transferred. So what we found out was, with a trace amount of ammonium sulfate and sodium chloride, we could reverse the sign of the charge transfer from that of the pure water. And also we found that the magnitude of the charge is also slightly higher. So I'll show you the cloud which is actually occurring in this chamber. I've cut short this video. So this is a video of a cloud which is now, initially it is water vapor, and small droplets will be there of about 5 to 10 micron cloud droplets. And then at some point of time, we will initiate the ice phase in the clouds by introducing some liquid nitrogen into it. And so slowly crystals will start forming in this cloud. And these are the 2 tubes which you are seeing, which you had seen in the chamber there. The top tube is having a graupel, and the bottom tube is having a slide for sampling. So now crystals have started forming. You can see the change in the color of the cloud, because crystals have started reflecting more light. And these crystal sizes and the droplet sizes are exactly of the same order which you see in a real cloud, because these crystals, ultimately they grow to a maximum of about 120 micron in size. And the graupel we have used is about 2 millimeter, 4 millimeter, and 6 millimeter in size. See, the crystals are growing bigger now. And droplets we can get from the size 10 to 30 microns, which are the cloud droplets. Typically, that is what you have in the cloud. So we have some levitation going around in the cloud. So that is why whole thing is moving up. So crystals are growing bigger and bigger. So at certain point when there are only
So it seems it has disconnected. Hello? Mohan, can you hear me, Mohan?
Yes, please.
Yeah.
Hello.
Yes. Can you hear me?
Yeah, I can hear you.
Yes.
Sir is disconnected, right?
Yeah, looks like.
Okay. Okay, the problem was on the other side. I thought it is my personal problem.
I think internet or other issue maybe.
Laptop, but it was. So is it okay now? We can see you and hear you. But Pradeep Kumar is missing, Doctor. Pradeep Kumar is not seen yet. In the meantime, Dr. Ghulam Rasool Sahab had joined. I can see him. And we have lost Pradeep Kumar, yeah?
Yes, sir.
But what Dr. Rohini? Maybe she can inform him. Dr. Rohini is also missing.
Yeah. They have some issues, network issues. Looks like. Can we request Ghulam sir to speak?
Yeah, he can speak now at the end of the lecture. That will be better, no?
Because it's already 4:10, I think. Where the lecture.
Some lecture still incomplete, no? Lecture is not yet over, right? At least Pradeep Kumar should be there. Good. Ghulam Rasool Sahab, can you hear us? Your mic is mute. Can we see your video?
Yes, sir.
Yes,
Thank you. Thank you very much and very good afternoon.
Good afternoon. We just got interrupted in between because of the network problem. And hopefully, network is restored, but we have lost our speaker.
Yeah. Yeah, this is technology.
So we hope that he will join in a few minutes. And then somehow there was some confusion because initially I requested you to deliver your remark at the end of the talk, but in the program flyer it was placed in the beginning of the talk. So there was some confusion, but it doesn't matter. I mean, you can give your remarks when the lecture is over. Still, we are waiting for the speaker to get connected. So let us see. I think maybe about 10 or 15 minutes may be left in this lecture. And today is the last lecture of this series. So it might take a few minutes more to conclude.
Yeah, he joined, sir. He joined.
Oh, yes, come.
Yes, sir.
Yes, join.
So,
Yeah, good. We lost you, so now we have got you back again, Professor Pradeep Kumar.
hello.
Yeah, we can hear you.
Can you hear me? My computer conked off, so I came to Rohini's computer.
Is, I think, oscillating, but we can hear you. It's not yet stabilized.
Okay,
You can start projecting, sir. Yes.
Okay, let me
Share your screen.
I have, wait a minute. I have to open my.
Okay, now your screen is stabilized. So you can share the PowerPoint and resume from the point where you were lost.
Yeah, I was just lost only 2 slides.
Okay.
Okay.
Okay. So,
Yeah, I have to run from my room to her room.
yeah.
I have to share the screen. Na?
Yeah, you have to share the screen, yeah, please.
How do I? Yes. Now I have to first.
People are finding your lecture very interesting, especially today's lecture on atmospheric electricity
Yeah.
and charging of the clouds are very, very appealing to the participants. We're getting feedback on the screen.
Okay. Okay, now I'm sharing the screen.
And today I see that
Yeah.
we have,
Has it come now?
yeah, it's coming up. Yes, now it is visible. Your screen is visible.
Okay. Now it is okay.
Yes, now it is visible.
Okay. So I was showing that is almost
Yes,
over
yes.
now, the video.
Right.
So now I'll come to the charge development in a mixed phase cloud.
Right.
You have this, now I told you that is in the Saunders and Takahashi, they have got the charge reversal temperatures at around -18 or something. So now that's why I'm put 2 different charging zones here. So I have a mixed phase, which is an ice crystal, and this is my Graupel, and this is all the supercooled droplets are here. So now when they are coming closer together and colliding and bouncing off. Now in this, above the charge reversal or below the charge reversal temperature, the Graupel is getting negatively charged and the ice crystal is getting positively charged. Ice crystal being lighter is going up. And above the charge reversal temperature, the Graupel is getting positively charged, and Graupel being heavier is coming down, and ice crystal being negative is going up. Okay, this has gone up. Graupel has come down. This region ice crystal. So this whole entire middle region, you have got a negative charge building up, and top region you've got the positive charge building up, and a small pocket positive charge which is coming up near the freezing level. So this is a broad picture of how the charge will be developing, which is we call it as a dipolar structure that is positive and negative. Pocket positive charge, normally people don't give much weightage to it, but it is important for the cloud to ground lightning discharge to happen. Okay, so this is basically this one. Then so you have the lightning discharge, in cloud lightning discharge happening between my negative centers to positive centers. And then you have got a cloud to ground lightning discharge, which is first initiated between the main negative charge center and the small pocket positive charge center, and coming down as a cloud to ground lightning discharge. So now numerical simulation of electric field using charge parameterization scheme of Saunders. So this is a work of an Israeli group, and the whole Saunders experiment of 40 to 50 years. What they have done is, in terms of the effective liquid water content in the cloud and temperature, they are divided into 9 different zones. And these are the parameterization equations made for or developed for different zones depending upon the temperature and how much charge is separated in those regions. And so these 9 parameterization equations, using a RAMS model, regional atmospheric modeling system, they simulated a thunderstorm over the central and northern Israel. Okay, So this is the charge development of that particular storm which they have simulated. Negative charge is at the top and positive towards the base. Okay, base is around, this is around 2 kilometers. So base is coming to around 1 kilometer. You have the charge which is developing, positive and negative, and this is the field which they have calculated. So after about 24 minutes of simulation, once this one storm has started building up, it is reaching a breakdown field. The breakdown field is about 300 kilovolts per meter, which is the required breakdown field for the lightning to happen. So like this, the numerical simulations can be done using the by parameterizing the equations from the laboratory. So now the take-home message: atmospheric electricity can be split into fair weather and disturbed weather. Fair weather I have touched upon very little. Fair weather itself is a very huge topic. I have touched upon only a very few this one components which are required. Then lightning occurs during disturbed weather. It can be inside the cloud, in cloud, between two clouds. We call it as IC discharges or cloud to ground lightning discharges, and the breakdown electric field required is 300 electric volt per meter is required to produce lightning. Return stroke in the cloud to ground lightning produces the largest current, and disturbed weather is driving your fair weather electricity. That is far away from the thunderstorms. Whatever electricity you are seeing is driven by the disturbed weather. And upward discharges from the thunderstorms occur in form of transient luminous events, which are red sprites, blue jets, and blue stratus. These are the only 3 events that I have touched upon. There are some more, a few more, which you can see in the ionospheric altitudes, much higher altitudes. So the electromagnetic radiation produced by lightning is used by the lightning location networks to exactly find out where exactly the lightning has happened, and there are so many uses of it. And lightning is also observed by satellite using the lightning imaging sensors, which uses atomic oxygen pulses emitted during lightning. And there are a number of charging theories to explain the charge development in thunderstorms. And the most accepted theory is the charge transfer during collision between ice crystal and graupel in the presence of supercooled droplets, and field observations also support this theory. Number of laboratory experiments have been conducted to study this theory. Parameterization equations developed in the laboratory experiments have been used in models. So thanks to my present and former students for providing me with pictures and videos of lightning. All these students have given me the lightning videos and pictures, which I have shown it in today's lecture. Important references you can see is Lightning by Martin Oman. It's a very good book. And this is a very good review. Charge separation mechanisms in thunder clouds by Clive Saunders. It is in Space Sciences Review, published in 2008. So, thank you.
Thank you very much, sir, Professor Pradeep Kumar, sir. Sir, we will take up the questions now, or we will have.
Yeah, we can take up the questions.
Yeah, yes. Mohan, can you take up the questions?
Yes, actually, there are many questions. I think all the participants enjoyed the sessions very much. Sir, very first questions is related to the. She asked, it is very informative lecture. Is there any satellite-based sensor to capture red, spirit, or blue jet images?
No, there are no. I don't think there are any satellite sensors.
Sir, I think your sound is not that much louder. Could you please check?
I don't know. I'm sitting on Rohini's computer and she's not here.
Now it looks good. Yeah, it sounds good.
Is it okay now?
Yes, sir. Yes, sir.
Okay. Okay. So it's only
Mohan, you can go there.
because it has to be done through the videography. So that is why the pictures which I have shown are taken by the astronauts on board the International Space Station. I don't think there are any on the satellites, because satellite is only the lightning imaging sensor, and that is presently it is not there. Okay.
Sir, or you can try with switch off the video then. It's
No,
still
Mohan, his sir voice is fine. Sir's voice is
Yeah.
fine.
okay.
Can you
Fine,
hear?
fine.
Please
Okay,
proceed.
okay, yeah, now okay. Yeah, sir, next question is red spreads are in upward direction. Why red spreads are in upward direction?
Red stripes are in upward direction because see, these are happening, basically these are excitations which are happening from the atomic oxygen and the nitrogen which are there in the gases which are there in the atmosphere. So when you are, it's basically when the lightning is happening below, you are integrating the whole field. From the surface to the top of the atmosphere, the electric field when it is integrated. So that has to reach this potential for the excitation to happen. So that is happening at that when you are going higher in this form, that is when it is more or less in the atomic oxygen levels. That is it is happening there. Because down below you have a lot of pressure is very high, and also mostly it is in the molecular stages. You don't have the atomic level gases which are here. Upper levels you are having. So that is why the excitations are happening. They are basically excitation. Something similar to your night glow, day glow, which you have seen, which all are upper atmospheric phenomena.
Okay, sir. Sir, there is two questions from Yaeli. I
Maybe
need to
Professor
ask about the
Professor Pradeep Kumar can stop sharing his screen. Probably that might.
Yes, sir.
It is not.
Okay.
Okay. The question is of lightning and thunder with the Earth's surface. In his or her country, there is a common belief by most people that when lightning strikes in certain surface, it can collect some precious minerals like gold, and there will be abundant gold or diamond plates deep at a striking point. Some people also believe that those precious metals are brought from atmosphere together with a striking thunder. I think such a belief may also be in India. Could you share some scientific thought?
It's not brought
Since.
from it's not bought from the sky. See what I've given you the values of temperature it can heat. Okay, basically it is a high temperature which is striking and the high current which is flowing through that. Which is, so heat is of the order of average value is 30,000 degrees Celsius. So it could be much higher. So what is happening could be anything which is forming is because of the heating which is happening. High heat, high pressure, which is generated by these channels. I have not personally not investigated into any of these lightning striking spots.
No, he is asking whether God is sending gold and diamond.
No, God is not sending. God is sending only the current and so it is possible because possible means because you are putting in high current and high temperature and high pressure. So there
Yes,
could
sir.
be formation or change in the chemical constitutions happening. Because lightning is one phenomenon. Lightning is a phenomenon which is people that is who study the development of the present day atmosphere from the ancient atmosphere. They invoke this lightning. The lightning is there in several planets. Several planets observe lightning. Like in some of the planets, it is because of the ammonium gases. And lightning even happens in volcano, which is because of the sulfuric sulfur gases. So lightning is a phenomena which is happening, charge development which is happening in gases, and constituents can change. Okay.
Okay, sir. Sir, can using electronic device like television, computer while it is raining or increase the probability to be hit by thunder? Though it is raining in his place, but he is using laptop. So actually, it's related to precautions.
No, it is not. It cannot generate or this one thunder or anything. But it is better to switch off your this one because when lightning is happening, like I told you, it can send you surge currents, and surge currents can be very high. So that is why they say that is you please remove the. Even if your computer or television is switched off, they ask you to remove it from the plug itself, disconnect the line, because surge currents which are coming can completely burn your electronics which are in the system. So like television and this one laptop and mobile, they cannot induce any thunder or lightning, but it can be ruined by lightning.
Okay, sir. Sir, Mr. Jiban Bhandari want to know how the solar space weather activities affect the thunderstorm and lightning in ionosphere and its nearby region. Is there any strong impact of solar flares recorded in tropospheric region of the Earth?
No, no, there is because only this when you look at the coupling of currents, because they when we call it as the global electric circuit, where the lower atmosphere couples with the middle atmosphere and the middle atmosphere couples with the upper atmosphere. So it's all a coupled system of the currents, with the lower atmosphere having the maximum generation in these all three regions, because megawatts of power is generated by the thunderstorms, whereas it is kilowatts only in the ionosphere and the magnetospheric region. So when you are looking at the coupling of the currents, only then your the solar flares and the phenomena is going to affect. It's only the coupling. Coupling is that's all, because otherwise it is not going to directly influence your formation of lightning or thunderstorms or anything. It's only the currents which are coupling that will be influenced. That's all.
Can you please explain the tripole charge structure with respect to varying LWC in the cloud as shown by Takahashi's group?
No, I think he'll have to read the papers, because it is too large a topic. I'm telling you, these are all summarized of 40 years of work. Several PhD students have done their work. Several postdocs have done their work. Even as a postdoc, my 2 years I have contributed to the Manchester group. So it's very difficult to go into in-depth into anything. Not in the short lectures.
Sir, is there any relationship between cloud-based height and cloud ground lightning?
Yes, the higher the base, the lower the chances.
Why some cloud have inclined bases?
Clouds have inclined bases. It could be due to various reasons, maybe due to the wind shears, the topography. It's not due to one thing alone. There could be several things which are affecting making it have inclined bases.
We are on almost end of the questions, and maybe one or two which remain. Why can't we harvest lightning produced energy for our domestic use?
No, you can't, because these are only momentary phenomena, and these charges are not there like these are all integrated in a volume. So on each of these particle which you are taking, and that is maybe the rain particle or the graupel or the ice, it is of the order of femtocoulombs, 10 to the power of minus 15 coulombs. So only when you are integrating in that large volume, you are getting about that 20-30 coulombs. So these are not charges which are there. Okay, there was so you can't harvest this.
Sir, final question is related to the lightning damages coconut trees in many orchards, which is the great loss to many farmers. Is there any solution for this crop damage?
No. Coconut trees, all tall trees can get hit by lightning, because the lightning always strikes the tallest point, because that is where the electric field is concentrated. Because if you're a physics student, you will know that between two parallel plates, the field lines are straight, and if you put any point, the field lines are curved there, and the field intensification happens. So that is why it always strikes the tall point, because at the tall point, the field is intensified, and there is no way to save any coconut tree or anything. Whatever is getting hit will get hit.
Sir, thunderstorm is a tropospheric phenomena, and we all know that it produces lightning too. Is there any contribution of ions present in thermosphere for contributing current during thunder?
question. What he wants? Ions? Ions.
Is any contribution of ions present in thermosphere for contributing current during thunder?
No. There is no contribution of ions in the thermosphere to the lower atmosphere for lightning.
And from that we harness energy. Okay. Sir, some cloud-free zone present in atmosphere. Why there are some cloud-free zone present in atmosphere?
Cloud-free zone, because for cloud to form, you need to have moisture, and you need to have upward. You need to have the updraft. That is, it should be rising motion. If you have got a sinking motion and no moisture, you don't have any clouds. And for clouds to form, it should have the dew point temperature. Proper dew point temperature should reach with that moisture, amount of moisture. So in regions of subsidence or where there are moisture level is very low, you don't get the clouds forming.
Sir, these are the questions. I think as much as possible we already covered.
Okay.
So Lakshmiji, over to you. Thank you, sir, for your insightful description and attend all the questions.
Well, Dr. Lakshmi Kumar is probably temporarily away. He will join in about 5-10 minutes. He shared the message to me. So in the meantime, Tagi Saab is there? Tagi Saab, are you there?
Yeah, Somesh.
Yeah, sir. Yeah. Ghulam Rasool Saab aa gaye hai, so we can now have his remarks. Right?
Yes. Welcome. Let's have him and
Right. Yeah. Well, for your just information and also for the audience, let me say a few words about Dr. Ghulam Rasool Saab. Dr. Ghulam Rasool Saab is the former Director General of Meteorology of Pakistan Meteorological Department. He is also our member of the Executive Council of SAMA from Pakistan. I think after his retirement, he also worked for a few years at EC Mode. There is the International Center for Integrated Mountain Development in Nepal. Now he's back to Pakistan. So for your information, sir, I just let me tell you something about lecture series, because you were not there in the beginning when we generally describe about this lecture series. For this lecture series, we had more than 2,000 people registered from 48 countries. Basically, besides our 9 countries of SAMA, since these lecture series are also open to the member countries of our institutional members, like EC body is institutional members and RIMES is an institutional member, and so also the NAM, the non-aligned movement countries, science and technology, they are also our institutional members. So by virtue of that, this lecture series, which started on 7th of January and is ending today, we have completed 16 lectures, 1 lecture per week. This lecture series was open to the people of all those countries. So about 2,000 people from 48 countries, they registered for the lecture. On a given day, about 100 people, attended. Today also, I think the maximum probably 125 people were attending this lecture. Some of them are from South Africa and somewhere in the forest like Philippines. So the time zone which we are having 3 p.m. in India. For many others, this 3 p.m. is not very convenient. Somewhere it is night time, somewhere it is early morning. So many of them, they are not able to attend live. But all these lectures, this 16 lectures that we have conducted as part of this series of lectures on atmospheric physics. In fact, they're all available on the YouTube, and people can view the lectures on YouTube, even if the lectures are over, which people are doing, because we can see the number of viewers increasing day by day for all these lectures. The first 4 lectures for this series was on basically orienting the people who are not from the background of meteorology, because this lecture series is meant for people from all these countries having just postgraduate degree or professionals of non-meteorological background who are interested in learning the subject of weather and climate sciences for research and operation purpose. So many of them, they do not have the background there, and therefore we had 4 orientation lectures in the beginning to introduce this subject to the people about what this atmospheric science is, what is the scope of that, what are the observation techniques, etc., etc. So there were 4 orientation lectures in the beginning of this series, and that was followed by 4 lectures on atmospheric thermodynamics. It was given by Professor Bhaskar Rao, who is the emeritus professor from Andhra University, Volunteer, and that was followed by 4 lectures on atmospheric radiation. It was given by Dr. Mukhopadhyay. He is retired ADGM from India Met Department, and then the lectures on radiation was followed by 4 lectures on cloud physics, which is given by Professor Pradeep Kumar, emeritus professor from University of Pune. So with this, we have completed all the 60 lectures of this current lecture series on atmospheric physics. Of course, in future we shall conduct next series of lectures on atmospheric dynamics, hopefully, after some time. And we have planned that at the end of the series of lecture that is today, the last lecture of this series, we shall conduct an evaluation test next week based upon the performance of the evaluation test. The participants will be given certificates also about the merit certificates, and also we are counting the attendance who have been attending the classes regularly, and especially those who have attendance more than 75%. They were already given the appreciation certificate after I think half of the lectures were over. So in fact, there will be 3 types of certificate. One certificate to all those who just participated, they will get a participation certificate. Second type of certificate will be given to those who have attended more than 75% of the lecture. And of course, the third one will be given to those who perform well in the evaluation test, which will be conducted the next week. So 3 types of certificates will be given for this. So this is about the background of this lecture series. And with this background, I would like to request Dr. Kumar to give your remarks about this. So on to you, sir.
Thank you very much, Professor Das and Professor Jeet Tyagi Saab. Very good afternoon, because I was a little bit late when I saw the today's program. It was different as compared to the email I last received. So therefore, I was a little bit worried I should not miss this lecture. Last part of Dr. Pradeep's lecture I have attended, and it has nicely been presented. Very complicated ideas have been presented in a very simple way, which could be understood by the professionals from meteorological background and non-meteorological backgrounds. This is a wonderful experience. Thank you, Dr. Pradeep, for refreshing our knowledge also. Long time ago, we studied this atmospheric thermodynamics and atmospheric electricity. More than 2,000 participants registered, and from 48 countries. This shows an amazing interest of professionals and practitioners in weather and climate science. This is quite encouraging. I have gone through the titles and contents of last 5 lectures which have been delivered. And I found a nice balanced learning for both professionals from meteorological background and non-meteorological background. And this is in fact the art of these experts who have made it so simple that both the communities should benefit from this knowledge. I'm very, very happy that SAMA has become a great knowledge platform in a very short span of time. We are just a few years old, but this is amazing that a lot of people, even early career scientists and the professionals from other backgrounds who are working with environmental sciences, they are benefiting from this knowledge resource. I hope this initiative will continue with new topics and so many other things. I would like to suggest that in addition to this hardcore science topics, we should move on to the awareness of public also. Some of my professional experiences, which you will agree, that under critical weather conditions, sometimes there are rumors which are contradicting the verdict of meteorological services. So those are presented in such a way that public is tending to believe them. Those are not true. Those are rumors. On this issue, we should work hard, and from SAMA's platform, there should be some lectures. With those lectures should clarify how authentic meteorological services products are, how they are prepared, how much they are science-based, and how authentic they are, so that the public should use these products with confidence, and rumors should be eliminated. I have seen in tropical cyclone era and in heat wave era, some YouTubers, they are also issuing forecasts along with meteorological services. And those are creating panic instead of presenting the realities. This is a front where we have to work, and we should present the methodology, procedures followed by meteorological services, so that public should be confident in choosing the warnings and information. Another issue is NWP products. NWP products are many, and they can be used by almost all the users who are interested in weather and climate sciences. So those products should be presented in a simple way, and the ways how they can be used by water sector, by agriculture sector, biodiversity and disaster risk reduction, and also some introductory topics. I believe in first 5 lectures, as Professor Das mentioned, these things might have been covered, but when we will be just following the flow of knowledge, we can make these things more clear. And impact-based forecasting, which is now the topic which is most concerned, and people are more interested. They are not interested in that tomorrow there will be rain, tomorrow it will be sunny, it will be windy. They are interested, if it will be windy, then what will be the impact of that windy weather for agriculturists for hydrologists, for travelers, or for the transporters, like that. So different communities have different interests. Likewise, when we touch upon climate change part, I believe that will be touched as we are progressing. Climate system dynamics should also be covered, and the components of climate system, how they are interacting each other, what is their feedback, and how they are resulting into a change. So these are some burning topics which were in my mind, and I wanted to share with you that these should be also covered. And the selection of models, model biases, these are now the common things for those professionals who are working in other socioeconomic sectors and they don't have a meteorological background. This will be, I think, a great contribution if we make these things clear. Because I have seen in different conferences when a non-meteorological background professionals present these models or the biases, their interpretations are sometimes confusing, sometimes illogical. If we can put them on the right track, I think that could be a great contribution. Very well done, and I'm very, very happy. It was amazing 15 minutes segment which I have spent with Dr. Pradeep. I request all my friends to join me for a big applause to the architects of this initiative, collaborating institutions, those who delivered these knowledge products, and the participants who have shown interest and they are attending these lecture series. Very, 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 very well done.
Thank you, sir.
Thank you very much.
Thank
Over
you,
to you, Professor Das.
Yeah, thank you so much, Dr. Kalam, for your very kind and generous remarks. In fact, we are very happy to have you here on the final day of the lecture. Of course, this is not the concluding session because after this, the next week, we plan to conduct the evaluation test for the participants. And after that, after evaluating their answer sheets, when we get the results, then we shall declare it. And on that day, we'll have the final session in which we shall also invite all our EC members and AP members to attend the final session. So that will be the closing session. In fact, parallelly, in fact, this month has been very, very hectic for us because this lecture series was going on. And at the same time, we also conducted an online training on the WRF modeling system, which is truly difficult because that involves practicals on the NWP, not simply lecturing on the video. It is also involving the practicals, and it was really, really challenging. It was our first time experience. So, gradually, of course, we will be conducting the trainings and workshops on other subjects also because, as you know, we have got 7 scientific committees of SAMA, including education and outreach. In fact, this lecture series is part of the education and outreach committee of SAMA. Then the next stage, NWP, which we have already conducted the first training course based upon the feedback received from the countries. Then the next one would be, of course, on satellite meteorology. Also, we have had the meeting of the satellite meteorology committee and then got their feedback. So based upon their feedbacks, we shall conduct a training on the satellite meteorology. Then the next committee on radar meteorology. The next is on mountain meteorology. We had the meeting of mountain meteorology in Nepal and just 2 months ago at DHM, Kathmandu, Babar Mahal. And then the other committees like air pollution, climate change, which are still in the pipeline. So with whatever limited resources, as you know, we have got zero budget, zero funding. support from anybody. And despite this limitation, we have conducted more than 54 activities of SAMA since its establishment 2.5 years ago. So we will be conducting gradually all these things. Just 1 minute. Tyagi Sahab, aap hai kya? Tyagi Sahab, are you there?
I am following. Please carry.
Yeah,
Please
we can
carry.
have a photo session. We can have a photo session, all of us.
Yes, of course.
Just give me a minute. Just give me a minute, please. Yeah, I'll just be back.
Miji, are you there?
Okay, I'm back. Yeah. So please, Mohan. Yeah, Dr. Lakshmi Kumar
Yes,
is not
I'm
yet
taking.
there. He has not yet joined.
Yeah, I think Lakshmi is not there.
Oh, it's okay. It's okay. So we can have the photos now.
Okay, sir, taken.
Done. So great. We still have 84 participants. And today, I think I saw peak participants were 125 or so. But some of them have now left because the lecture is over, main lecture is over. But still 84 people are still attending. So anyway, at the end, Tyagi Sahab would like to say something. Yeah, Lakshmi Kumar is also back.
Sir, one more photo session. Lakshmi ji is here.
No, take one more. Take one more.
Okay, done, sir. Oh, take it, sir, please.
Yeah. Well, I think Professor Somesh has covered almost all issues, and I'm thankful to Dr. Ghulam Rasool Sahib for joining us, though it was late, but he has given us point for considerations for taking up follow-up of this particular training program. We will be positively looking into the popular lectures for the users and also for non-meteorological professionals. And on topics like climate change, air quality. So all these are in pipeline, and hopefully we'll be able to cover up in the coming years with support from all our. See, the strength of SAMA is resource persons, the senior people who are extended all the help on our request. So that is our strength, and hopefully with their support we'll be able to deliver for the capacity building in the South Asian region, which is badly required in many areas. And that is what is the objective and the mission of SAMA. So thank you so much, Dr. Ghulam Rasool Sahib, and of course our Dr. very much to Dr. Pradeep Kumar, who has covered cloud physics in 4 lectures. All key aspects of cloud physics from precipitation to lightning have been covered. And I'm sure this will be helpful when we take up numerical weather prediction because atmospheric physics and dynamics both will be of great help. Thank you so much. And of course, the participation of a large number of students and young researchers, both from meteorological and non-meteorological background, I think is very, very encouraging. And hopefully our following programs also will attract the similar response. Thank you so much.
Thank you, sir. I think Dr. Lakshmi Kumar, some people were asking about the evaluation test pattern and things like that.
That we will mail tomorrow, sir, because anyway, that will be on 29th April, 3 o'clock for about 30 minutes to 40 minutes. And the questions will be 30 MCQs we will be giving. That we will have a small, talk over phone, and we will send an email tomorrow, sir.
Right. So, okay. So now, thank you so much, everyone, once again. And we can close today's lectures. Dr. Lakshmi Kumar?
Yes, sir. Thank you.
Thank you. So you are the host or I am the host?
You are the host, sir. You have to close.
I'm the host. Okay. So I have to close it, yeah?
Yes,
And-
yes, sir.
Okay, I just click the end.
You can stop doing live, sir. Otherwise,
Oh, I see. Stop doing live. How do I
go
click
to
on the
more.
live?
More 3 buttons are there. More 3 buttons.
Just a minute, more 3 buttons.